Okay, so let's get into Young's double slit experiment, which was an important experiment that finally gave some concrete proof that light behaved as a wave. So this goes back to Young back in about 1801. The idea was, well, prior to this, there was this Huygens analysis of light, which seemed to give to be able to explain light in a way that Newton could not. And so what was realized was, look, if light is a wave, then it should be possible, at least in principle, to see interference-like effects. So the simplest example is this so-called double slit experiment. And the way it was done back in Young's day was, I believe, using sunlight. And so it's a bit harder to make interpretations there. But the way that we'll sort of do a revised version of Young's double slit experiment is to imagine that you have a source of monochromatic light. Monochromatic in this case, means one color, but in general you could have a so-called monochromatic wave, and that would be waves that all have the same wavelength. So this is the idea that you send in monochromatic light into towards a material that is basically completely opaque except for two small slits, and then you are going to observe what happens once the light makes it through those slits and gets to the other side. So the way that this looks like, if we can imagine, this is a wave-like phenomenon. So I guess backing up a second, if light is totally describable by rays, you can imagine light coming in, it takes the form of rays. And then on that screen behind it, you would not anticipate seeing any kind of interesting interference type behavior. You would just expect to see two dots or two slits that correspond to the slits through which the light went. On the other hand, if light is made of waves, or if it's describable by waves, then you might expect to see something on the screen which is more interesting, not just two slits, but maybe something more complicated. So before I show you a picture of what this looks like, we should at least have a sense of what should happen. So I'll show you this picture, and then I'm going to try to justify it for you. There's a characteristic, there's a few characteristic lengths here. One is d, which is the spacing between those two slits through which the light travels. L is the distance from that double slit setup to the screen onto which the light is projected. And crucially, we will almost always have that distance L to be much longer than d. So d might be something that is comparable to the wavelength of the light, which is only several hundred nanometers, whereas L might be a meter or several meters. And then what you will notice that if we have a wave, we should end up with an interference pattern that depends on the distance, specifically the difference in the path lengths from one slit to the other. So now let me draw you a picture to try to justify why that is the case. So let's go back to the example of sound wave interference, and let's imagine that you've got two monotone speakers set up. So two monotone speakers, and we'll have them nearby each other. Monotone speakers. They're both playing some obnoxious 440 hertz sound or something like that. Here's one speaker, I'll call it S1. And it's emitting sound, and let's suppose that you are here listening. There's your ear, and sound waves are going out of this thing, and of course sound waves are purple. So here we go, sound wave, a single monotone. I don't know why you're smiling, because it's actually an obnoxious noise. Now imagine that you've got another speaker playing the same sound, and it's coming out at the same time, but this is offset, and it's back, let's say, over here. I want to draw it so that it's just behind speaker number 1. So here's speaker number 2. You can imagine that it's emitting a peak when that one's emitting a peak, etc. And its pattern of wave will look like this. I'm trying to draw it right. Now, this is just one example of the kind of thing you might hear. And I'm trying to imagine, you have to imagine that it's oriented such that it gets to your head at the same time and in the same place. So let's imagine this is your giant ear, and you're hearing them both at the same time. Now, suppose they're offset by some distance x. That is to say that the path length that the waves take to get to your ear are different. That is to say, speaker number 2, the waves coming from that speaker are taking a longer path by an amount x. As I've drawn it, you'll notice that although the individual peaks from each speaker don't line up, it doesn't matter. You still get peaks lining up with peaks, troughs lining up with troughs. This example would be constructive interference. And if you think about it, I can even bring back speaker 2 even farther, so long as the distance, there's the path distance difference between them. If it's equal to 0, then of course you'll get constructive interference. If it's longer by one wavelength, or frankly, if it's shorter than by one wavelength, so plus or minus, or if it's longer by 2 wavelengths or shorter by 2 wavelengths, you'll also get peaks with peaks, troughs with troughs to get constructive interference. So the general statement you can make is that if x is equal to any integer m times lambda, then you'll have constructive interference. On the other hand, you could picture the second speaker being offset by half a wavelength. And let's just draw that picture. Another example. You got S1 over here and S2 over here. Speaker 1 making its nice 440 hertz or whatever the sound is. Now imagine this one is making a sound that does this. So its trough lines up with that peak, its peak lines up with that trough, etc., etc., more or less. And then by the time it gets to your ear, in principle, if it's perfectly set up, you will get completely destructive interference. Again, peaks line up with troughs, or if like a positive cancels with a negative. Remember, these waves simply add up due to the principle of superposition. So destructive interference occurs, and perhaps I should say perfect destructive interference, but that's okay. Destructive interference occurs if, and now remember that we're calling this distance x, if x is equal to, well, if it's offset by, a wavelength over 2, a half a wavelength, that's the distance from a peak to a trough, or if it's shorter by that amount. And we already said that if it's shorter or longer by a full wavelength, you get constructive interference. But again, if you then extend that another half a wavelength, in other words, if this is bigger or smaller than 1.5 wavelengths, or 3/2 of a wavelength, or 5/2 of a wavelength, etc., then you get constructive interference. In other words, if x is equal to, you can write this as some integer m plus 1/2 times lambda. That is the situation for constructive interference. So let's go back to this picture. What's being described here is, at least in figure A, is what happens along that center line. You get the brightest signal, or if you like, if it was sound, you get the loudest sound, or if it's light, you get the brightest amount of light. And that would occur when the path length from the first slit or the second slit is equal. On the other hand, or if you like, in addition to that, you'll get other spots where it's bright, as long as you move far enough up that the path length from the first slit and the second slit are offset by a full wavelength. On the other hand, if you look at a spot where that path length from the first slit and the second slit is offset by half of a wavelength, then you'll get a dark spot. In other words, you'll get destructive interference. Now there's some geometry that's being discussed here, and I'm probably about to just redo it, but that's okay. So let's see what this looks like. So now we have our conditions for constructive and destructive interference. Let's make sure we can understand the geometry. You have these plane waves coming through. They hit this mostly opaque board, but then there are these 2 tiny slits separated by a distance d. And over here is a screen. This might be like a photographic plate, or just some, dark background, a dark board on which the light can be illuminated. So the slit spacing is d. The separation from the slits to the screen on which it's being propagated is L. I'm going to use a capital L, just because that's already how I have it set up in my notes. And it's not drawn to scale. What you have to imagine is that L is much bigger than D, and that will become important in a moment. So we already know that we expect to have a single bright spot along the center line, which is this line of symmetry here. Let's just indicate a direction. Let's call this the y direction, and this will be a position of 0. And now what I'm interested in knowing, yes, of course, the brightest spot will be here at the 0 mark. But the next brightest spot, which, by the way, should occur above and below, let's indicate that here. Let's sort of guess. It's going to show up somewhere like this. This is if, of course, light is made of, it can be described by waves, and it can. So let's call this the next bright spot, or bright fringe, if you like. So here's one, and then here's another. Okay, so the way that we're going to figure this out, and this will now confirm what you have seen in your book, is that we'll draw a line from the first slit to that bright fringe. That's not terrible. Let's draw another one from the second slit to that bright fringe. And then what I'll do is just indicate one more thing. We're going to describe that there's an angle here, and I'll do that with orange. Imagine that we're measuring the angle by drawing a line from the center between the two slits. And as it turns out, sort of the angles here are all going to be pretty similar if L is much bigger than D, but let's indicate this as being the angle theta. Now, the path length from each of these slits to this bright fringe are not quite equal, but they are close to equal. And let me just point out to you where it would be equal. If we can sort of cheat a little bit and make this an equilateral triangle, notice that if I draw a line from here to here in such a way that I make this angle equal to this angle, that would be an equilateral triangle. No, sorry, an isosceles. Forget the names of these damn things. I think it's an isosceles triangle. Anyway, pick the angle such that this path length is equal to that path length. Then you'll notice the amount that they are different is that amount, which I'll call x, consistent with our notation above. Now, the fact that this is the angle theta there, it turns out you can show that this is also the angle theta. Which means that, given our setup, we should be able to conclude that that triangle, given that this is in fact a right triangle, you can show that sine of theta is simply equal to, it's the opposite over the hypotenuse, in other words, x over d. Okay, so remember what we had said, if you're interested in a bright fringe, that occurs when x is equal to m times lambda, where m is an integer. In other words, this is m lambda over d. And therefore, you get to the equation that you will certainly find in your book, that is d times sine theta is equal to m lambda. That is a condition for a bright spot in the Young's double slit experiment. Again, I'll call this bright spot or constructive interference. Maybe I'll just call it bright fringe for double slit. Now, from this, you can sort of immediately conclude, well, what happens if I played the same game but instead looked for a dark spot? You would not have the condition for x being equal to m lambda. Instead, it would be the quantity m plus 1/2 lambda. So you can immediately conclude that d times sine theta is equal to the quantity m plus 1/2 times lambda for, I don't know if it's called a fringe. I'm going to call it dark. Yeah, sure, I'll call it a dark fringe. It's a dark spot, whatever. Again, this is for the double slit. Okay, good. The last thing to point out is that we can also predict where the position of these bright and dark spots will appear on that screen very, very far away by doing just a little bit more geometry. You'll notice that I'll use light blue to show you that there is a secret right triangle here. Notice that this is one side of a triangle, this is another side of a triangle, and this is the hypotenuse of that triangle with the angle theta. In blue, then, I'll notice that sine of theta can be written as, well, the distance from that central bright bright fringe to the, for example, next bright fringe. I'll call that the position ym, m referring to which bright fringe it is. That is the opposite side, and then the hypotenuse, that's this here. Well, that is given by the square root of L squared plus D squared. But remember, I'd argue that whenever you're doing these experiments in real life, you're always going to have tiny slit spacings D and very large distances to the screen L. In other words, L is so much bigger than D that this is approximately the square root of L squared. In other words, take this and neglect it, in which case this is approximately L, which means that the sine of theta is approximately equal to ym over L. So another way that you can write this bright fringe equation, and this will be useful when you're asked to find the spacing between bright fringes, is you can write, instead of sine theta, you can write basically ym over L. That is approximately equal to x over d. In other words, m lambda over d. And maybe I'll just sort of box it there. Again, that is for constructive interference. Or bright fringes, maybe I'll just say that. And I'll leave it up to you to determine what the equation would be for the dark fringes. Now, what does this look like? If you suppose you shined red laser light through two slits, what would you see? It turns out you actually do see an interference pattern, so there is a valid wave description of light. And as is being illustrated here, so what you see is a series of bright spots, dark spots, but they're not all the same brightness. Even the successive bright spots become less and less bright as you move away from that central bright spot. But you do notice that they are more or less spaced out evenly. We're going to do an example in just a minute. I do want to go back and point out one thing. There's a terminology here when you're asked to find the first order, second order bright spot. M equals 0, that corresponds to the central bright spot. That is this one right here. M equal 1 would be the next one over, this one, and m equal minus 1 would be that next one but below. So m equals 0, that corresponds to, let me, I guess, put this all in the same color just so I don't drive you completely crazy. M equals 0 corresponds to central bright spot or bright fringe. M equals 1 or minus 1 is the so-called first order bright spot. M equals plus or minus 2 would be the second order, etc.